Okay, well, thanks very much for having me. I wish I could be there in person, maybe next time. I know that you've already heard from Tim Ansel and Mohammed Kasim, so I hope there's not going to be too much overlap in the material. I am going to start with a little bit of a overview of my experience of using the open source ASIC tools as a user. And then give a little demonstration and highlight some of the interesting work that's come out of this field. So I'm going to share my screen now.
Okay, please.
And if you're into Twitter or LinkedIn, you can feel very free to connect with me. And also you can get these slides now or later on using this link, and I'll put this link at the end of the slideshow as well. So just a little bit about me. I work with quite a few different people in this space. I have a course called the ZeroToASIC course. We've had 200 people on the course, and about 40 people have made their own chips through working through the course. YosysHQ makes and supports Yosys, which is the synthesis tool that is used in all the open source ASIC flows. And ChipFlow is a new startup that aims to help product companies make their own chips. So if any of those sound interesting, then please either get in touch or go directly to the website. So let's start with a quick overview of what's happened so far. Things have changed very rapidly. We had the first open source PDK announced in June of 2020, along with the free shuttle opportunity. And it was the free shuttle opportunity that really got me on board. I'd previously used QFlow, which is another open source ASIC tool, to put one of my FPGA designs and get the GDS files, which are the files we send to the foundry to get the chips made. But the experiment kind of ended there. But with the opportunity to get free chips made, sponsored by Google, I got stuck in and was working on my MPW1 application. I talked about it at a conference called Remoticon, which is run by Hackaday. And there was a lot of interest, and that's what made me decide to start a course. And then we taped out MPW1 in December, and I did that with 4 other people. So we put 9 designs in total onto my MPW1 chip. 2021 saw validation of the tools with EFabless bringing up Strive and then launching ChipIgnite, which is a commercial version of the free offering. So it's $10,000, but you get 300 chips instead of 50. MPW2 taped out in June. We got the chips back in MPW1, but there was unfortunately some problems to do with a tool misconfiguration that led to hold violations. So if you're not a hardware person, then hold violations are one of the scariest types of errors you can get with chips, because they're very difficult or impossible to fix after you've got the chip back. If you've got setup violations, you can just run the clock a bit slower. So it looked like we weren't going to get any results out of MPW1, which was a real pity. But, you know, mistakes are made, and this is the first pipe of the new tool, so we weren't sure exactly what was going to happen. MPW3 and 4 taped out in November, December, and then there was this second Remoticon in November that I also presented at. And then we had great news in the beginning of 2022. With some careful control of the power supply, we were able to get all my designs on my first chip working. One reason why was because the chips were quite small. So there was a problem with the way that the clock was distributed, and on smaller designs with the correct voltage, you had a greater chance of them working. Whereas on larger designs, even if you got the voltage correct, probably things still wouldn't work. But that was great news for me, because I got all my designs working, including my clock, which is now on my desk. So that's nice. MPW5 taped out in March. We got the wafers out for MPW2 in April, but we're still waiting for them to be packaged and diced. We're just about to tape out on MPW6. So if you're really super excited by the presentations you've heard about this, then you've still got 1 week left to get your design ready. And then in the rest of 2022, we've got 2 more tape outs, we've got more factories coming online, and more open source PDKs. So lots of stuff is happening. It's super exciting. I want to talk a little bit more about MPW1 because this is the first chips that we've got back. John McMaster did this imaging, and he's also got a zoomable image on his website, so you can zoom right in. And if you zoom right into the corner, you can see the open source hardware logo. So super cool to see that in silicon. I also had my chips imaged by Olivier at TechSplained, who very kindly did them for me. And Maximo, who's Maxi Borger on Twitter, made this nice picture. He got a very nice macro shot and then put out all the different, what the different designs do on my MPW1 chip. And if you want to find more about MPW1, I've got this link here that I've been using to send when I send samples out to people. So that has all the designs, all the GDS, all the documentation that we've been working on. And I just wanted to include this lovely macro shot also taken by Maximo. So cool to actually get dies back with my designs on them, something that I never thought would happen as a electronics engineer 5 or 10 years ago. So yeah, like I said, all my designs are working. I have my clock on my desk now. It's a bit more complicated than I wanted. It should have all been on one PCB, but we needed this extra infrastructure to manage the voltage control. And I put in basically very simple demonstration designs, which ended up being a good idea because those simple designs were the most likely ones to work. So just a 7-segment counter, an LED driver, a reverse engineering capture the flag challenge that was originally written by a friend of mine, Q3K, and also the VGA clock. If you want more information about that, you can check this blog post. So I thought it would be a good idea because this is a RISC-V conference to look at how many RISC-V CPUs have been taped out. So it turns out there's quite a lot, nearly 240 RISC-V CPUs, although 200 of those are the kind of free ones because part of the application process, we get given a pad ring by EFabless. So the pad ring is all the I/O ports, but it also includes a RISC-V processor. And the first one was Pico RV32, and then from MPW2 to 5 was VexRISC. So then we had, out of 200 applications, the user area included 45 SoCs or CPUs, and 37 of those were RISC-V variants. So I've got a breakdown here. And here we've got a breakdown of what type of RISC-V CPU has been taped out. So we've got the big one, SCR1 and IBEX, but still quite a few VexRISC and Serve and all these other ones. So if you have a RISC-V architecture that you'll be interested in checking out on hardware, then there's other people that have done this before you can follow in their footsteps. So if you do want to do that, then I put together a video working with EFabless recently, which is a half-an-hour video that covers all the steps that you need from installing the tool chain to building a demo project and then submitting it. And you can watch that on this link here. And what I'm going to do is a demonstration now to show you what it kind of looks like as you go through the hardening process, where you take your hardware description language and then turn it into the files we need to send to the foundry. And we're going to do that using a tool called Openlane, which is one of a few tools that we are now able to use for open source ASIC hardening. The design goes in at the top here, runs through this loop and comes out at the end as a GDS. You can get the tools here, and I also built a summary program I'll be using to illustrate the different steps of this process in the demo. So first we do the synthesis, static timing analysis, and then we go into this middle part here. And this middle part is provided by OpenRoad, which is DARPA-funded open source ASIC tooling. And what we'll do is we'll come back to this. Actually, no, I'll keep on going through this. And then we do logical equivalence checking, routing, and then we extract the parasitics for resistance and capacitance, do a final static timing analysis to check that we can meet our timing requirements, and then stream out to GDS2, and we get those files. So the demo design I'm going to use is the 7 segment seconds that I taped out on MPW1 that you saw working in that picture earlier. You can get the repo here, and you can read more about how I got that design working on this link. But it's extremely simple. It's just a clock and a programmable clock divider with a bit of combinational logic to do the digit decoding. And the reason I wanted to use this was because it only takes about a minute or so to run. So let's switch to the terminal. And I'm in the Openlane directory now. And I've got quite a lot of designs here. And I've already put my 7 segment seconds design there. And if I show you config, you can see the configuration inherits a lot of defaults, and I'm doing some things here like giving it a different clock frequency. This is in nanoseconds, and then explaining to Openlane how dense I want to make the design. And then once I'm here, I can run this command design. Let me just show you the Verilog as well. So it's just some registers, a bit of sequential logic to do the counting, and then a bit of combinational logic to do the digit decoding. So very, very simple. And then I can run this demo. And things scroll past pretty quickly. And I can just pause the screen and scroll up here and show you, there's the STA we mentioned, and here's the Yosys output. So things fly past very quickly. All the logs get logged into a log directory. So here I am again. And if I do this, now I've got this Openlane summary tool that I explained about earlier, and I can say I want to use 7 segment seconds. This knows where all the files are. So if I just show you this, the run is still going, but we already have a lot of files there, 100 files, and so it's sometimes difficult to know which files you want. So that's why I've got this summary program. It is coded to know where things are. So I can first start off with Yosys. So that tells me about the synthesis. So that design ended up being 430 cells, and this is the cell breakdown here. And it also gives a rough idea of the amount of area it's going to need. I can also look at the top level synthesis, which only makes any sense at all with very, very small designs, because otherwise it just gets ridiculous. But this is now like all the different standard cells, how they're all wired together to build the hardware that I've defined that I want in my hardware description language. So that takes us to here. We saw the STA scroll past as well. Then we've moved on to floor planning. So let's take a look at the floor plan. So this is giving us the size of the die it thinks it needs, and putting the pins in place. If I measure this with a ruler, it's thinking about 140 microns. I'm getting a message in the chat with a coordinator asking me, can I share my slide again? Are you not seeing my screen? Then we've got placement. So that's global placement to start with. This is all those standard cells we saw from Yosys but they're not fitted correctly to the power lines. So the standard cells fit into these power lines. And then we can look at the detailed placement. And now all the cells are fitted to the power lines. And pick this up. So you can see there's still quite a lot of area, and by adjusting a lot of space free, and by adjusting the settings in that config file, we're able to squash this smaller. Sometimes it will take a longer time to do that though. If we just check on the other screen. So this flow completed successfully. Takes about a minute or so on my computer. And then we now move on through here, detailed routing, and the final part, the final thing that I can easily show you is the final GDS. So let's do that with this one. And then this is on the right here, I've got all these layers that I can turn on and off. And this is the final set of files that we would send to the factory. We've got the pins around the outside. And then here I've got the breakdown of all the standard cells again. So I can turn off the decoupling capacitors. We can zoom in and take a look. We can click on a cell to find out what it is down at the bottom, a NAND. That's a NOR 4 input NOR gate. We've got the horizontal wiring on metal 1, vertical wiring on metal 2, the power lines that we saw before. And this is pretty much, that's how that works. And then just as a final GPS 3D, I think it is. Look. There's a cool 3D program, which is for some reason isn't working right now. Okay, so that is a quick demo. And let me resume the slideshow. So how do you make a submission to EFabless? You've got that design now. Where does it go? So the way the chip is divided up, we've got this 10 millimeters squared of the user project area, and our design can go in there. And you see how small that design was. That was 140 microns, so it would be a very tiny square down here. Then we've got this management core that can be replaced with different types of cores provided by EFabless. And we've only got one at the moment, and it's this here, and it's based on VexRISC. So it has this RISC-V processor in it. So that's why I was kind of saying that every chip that's been taped out on the Google Shuttle has had a kind of a free RISC-V chip in it. So those statistics that I was talking about earlier, 200 of those RISC-V chips were the ones that came as part of the provided submission harness from EFabless. And then we have some information here, the UART, the SPI controller, the wishbone, the logic analyzer, and then our design goes in this part here. So if you want to make a submission, you need to go to the EFabless website. We've got the documentation there. Make sure to check out this video that takes you all the way through it. So that little design was very, very small. So it's a shame to waste all the area on the chip just with one small design. So one of the things that I've been working on with my course is some tools called the Multiproject tools. And they basically help me do the aggregation of lots of different designs, in this case, 16 designs. And here in this GDS, we've highlighted the activation lines. So all the projects get wrapped inside a little wrapper that adds a tri-state output to all the outputs. And then by bringing the active lines high or low, we can turn on and off the outputs from the designs. So that lets us have 16 designs all on one chip, but only one design is active at once. So we use this from MPW2 and onwards, and on MPW1 I used a slightly different type of way of multiplexing the designs with just a normal MUX instead of a tri-state bus. And so far we've submitted 70 different designs by 35 people across 5 shuttle runs. I also want to mention ASIC tools in the cloud. So Proppy has been doing some great work allowing us to do CMOS simulation as shown here, and also a full ASIC flow building to a GDS shown here on the right using Jupyter notebooks hosted by Google Colab books. So you can just click on one of these links, start the Python Colab, and then it shows a previous cached result before, but there's instructions at the top on how to get it started. And then you can roll all the way through and see your CMOS simulation. You can change the simulation parameters here, change these times, rerun the simulation. You don't have to download or install anything. So this is making things even more accessible. And the last project I want to mention is by Teo. You can follow Teo on Twitter here as well. And thanks to Tim Ansel for introducing me. He's doing very interesting work. He instrumented a RISC-V processor to count how many addition operators is used in a Linux boot. 65 to 72% of instructions use addition, so you should have a very, very fast adder in your CPU design. But there's lots of different adders you have in a CPU, so maybe you want some that are more performant than others. And at the moment with the Yosys synthesis tools, you get one type of adder. And Teo's work is allowing to map across this space and go for fanners that are more performant or more area or better or lower power. He did a lot of work on this, and you can check out his work here and on this link as well. So what I'm doing for MPW6 is taking the 4 different types of adders that he's made available and wrapping them in some instrumentation that allows us to precisely measure exactly how fast they are. So then we can compare the final size of the adder against each other and also compare how fast they are on real silicon and see if it matches up with what the tools predict. The last thing I want to say is that now is a great time to get involved. We've got a lot of momentum. It's a great time to jump in, join the Skywater Slack, come on my course, learn how to make your own ASICs and tape out your own RISC-V chip. What a cool thing that would be. So do get involved. The next tape out, as I said, is MPW6 later this, and then we've got MPW7 and MPW8 later this year, yet to be announced. Here's the link for the slides here. You can sign up to my newsletter for my course here, connect with me on Twitter or connect with me on LinkedIn. So thanks very much for your time. I hope you found that interesting. And I think we've just got a few minutes left for questions, if there's any questions.